All right. Hello, QuarkNet. We're here in the CMS control room. So I know some of you know me. I'm Darin Acosta, another mentor along with Frank. They're in the physics and astronomy department. I'll introduce my colleagues here. I'm Darin. This is Derek.
I'm Derek, Derek Grove. I'm with the University of Kansas. I work on the CMS experiment, and I'm a PhD student that's based here at CERN.
And I'm Collin. I'm also a graduate student. I'm enrolled with Rice University, working towards my PhD, also based here at CMS for the time being. I'm excited to show you around the CMS today.
Yeah, so for today, we're going to start here in the control room. Very soon, Collin will walk you around, see our shift crew and all the displays and things we have to do to monitor an experiment of this size. It's very complex, lots of detectors, lots of electronics. You'll get some impression of that as we're going around. Collin will be going underground. We can't take you in the collision hall. There is beams going in there, so that's not possible. But you will be going virtually underground to see where a lot of the electronics connections and other services to service the experiment. And so you'll get a feel for that and what it's like to go 30 floors underground and what's down there. So the machine itself and the experiment are deep underground at this point. And so you'll get to see that. I won't get ahead of myself. But yeah, so maybe at the moment, we're not actually taking data. The LHC is setting up to do some injection of beam, and then they're going to do some testing to prepare for heavy ions, Frank's favorite physics program here. But we have the crew all around, so you'll see all this activity, and I'll hand it over to Collin when he is ready, and he will walk you around where the shift crew works in the control room.
Frank, that is a technical thing. Oh yeah, you have already set it. Good.
All right, sounds good. Well, so here we are. I'm just a few feet over from Darin and Derek. We're in the control room right now. So as you can see behind me, we have the central shift crew. So these people man the detector 24/7 because ideally we'd like to be taking data 24/7. So everyone's responsible for a different part. We have people monitoring the detector safety systems, making sure that there's no that everything is operating safely, no excessive voltages or currents or leaks. We have a shift leader who is following the data, taking plans for the days, and making sure everyone's working together well. And then a whole slew of people monitoring the data taking. So making sure we're taking it at the right and appropriate rate, making sure that it's quality data, including different subsystems together. And these people do it in 3 shifts of 8 hours, so 24/7 a day. Yeah, so that's where we start here. And then in the back, there's a bunch of rows. I think you guys have been talking about particle physics and CMS maybe a little bit already. So, it's made of a bunch of different types of subdetector systems, but each one is a very complex system and needs experts that are on call and ready to troubleshoot any problems. And so this is where they work during the day, during working hours, and if there's any issues, they get called and have to get us back online as soon as possible so we don't miss any data. So this is where all the action takes place normally, and it's good to see a lot of people here since we're in the data taking period. But if we're ready, then we'll start making our way towards some of the other facilities here. We'll head towards the surface cavern or surface area where it was constructed above ground. So we can.
Going by the requisite coffee areas for all the shifters, people visiting, by the way, on his way.
And we also lost them.
And we might even have lost his signal, so you are stuck with me again. Yeah. So first of all, do you guys have any questions of what you want to hear about as we're going through and giving you this virtual visit to the LHC and CMS? Any questions so far? You're all experts now after your week of QuarkNet, aren't you? That's what I'm taking. That's good.
The
All right.
control room looks really very clean.
Well,
Darren.
that's
you
an
clean it
interesting.
before this visit?
So, by the way, that's something I should say. This is a new control room, just being used starting this year, I believe. So it's expanded. It moved out because the computers needed some real estate. So we abandoned the old control room to put more room for computers, but they've added a whole new building for this control room. So it's much bigger. We've got this central area that Collin walked you around. There's also another area for experts on each of the detector systems. But I'm going to hand off back to Collin because he's going to show you more things about the detectors in our experiment.
Right. So here I'm in the Peter Sharp room right now, and as I was just talking about all the different subdetector systems, maybe there's a nice graphic you've seen of the CMS. It's kind of like an onion with a bunch of different working subdetector systems, like the tracker. Maybe I can show you on this picture here. Here's a very popular one of the barrel region. And so collisions happen in the very center of our experiment, and then all that energy from the collision is turned into matter and new particles, and they work their way out radially. And so there's a bunch of different subdetector systems like the tracker down here, which tells us where the charged particles went. We can measure things like their charge and momentum, and then it works its way through two different calorimeter systems to try and measure the energy and capture all the as much of it as we can. And then this all happens within the eponymous solenoidal magnet. And then anything that makes it out past that should hopefully just be a muon. And we have a very large muon system made to track measurements of those as well. And so each of these subsystems are the people I was talking about earlier who have the workstations in the control room. But then also in this room, we have examples of each one of these detectors. So maybe I'll just give you a quick kind of review of that, or show you that. So the tracker in the closest to the interaction point is made up of a bunch of silicon pixels that are very, very small. So here's a zoom in on it from this microscope so that you can see that the chip is actually very, very small. In every square centimeter of this silicon pixel, there's 6,000 connections. So it's very, very fine detailed. And it tells us where a charged particle has gone. And so we can make very accurate tracks backwards. And then we can also see if a new particle travels into the detector and then decays, we should be able to find that vertex. And so this is really, really important system that for also debugging, or not debugging, but parsing out the very noisy environment when we get many collisions. But then as we work our way out, we have similar technology for like the strips. So it's also silicon, just a little less fine grained. And then we have the calorimeters, which I mentioned before, which measure energy. So you're not here, you can't feel it, but these clear crystals are made of lead tungstate, so they're actually very heavy. And there's and here there's a nice little thing you can feel the weight of them. Here is kind of a deconstructed hadronic calorimeter. This one's kind of fun. It's got a few fun facts about it. I mean, for one, it's made of very high quality brass, which is used to promote some hadronic interactions and hopefully break down the hadrons into particles we can detect with this plastic scintillator. But it's made from spent artillery shells from World War II that Russia donated, which, yes, yeah, here's a picture of the artillery shells, which is already a very interesting fact. And then also, which I thought might be interesting for the QuarkNet, over 400 of the readout electronics were made through the QuarkNet program with American high school students. So this is kind of an exciting detector for you guys to see. And this is, of course, a deconstructed one, but you can see where the energy is. These plastic scintillators collect light, and then depending on how much light is released, we can tell how much energy the particle had. But as we work our way out, there's the large solenoidal magnet. So it's made of it's made of these large aluminum blocks holding these small niobium titanium wires, which are superconducting, and they run about 18,000 amps during operation. So in order to run that much amps, we need to supercool it down to just a couple Kelvin. So it's 4 Kelvin. So it's very, very cold. But this produces a really, really strong magnetic field. It's about 3.8 Teslas, which is 100,000 times the strength of the Earth's magnetic field. So it's the strongest magnet of its kind. and the largest for sure. It's 6 meters in diameter and 13 meters long. So it's very, very large. And then hopefully by this point, most of the particles have been absorbed because we want to be a hermetic detector, but anything on the outside will be on the muon system. And so out here we have a bunch of muon detectors. There's a bunch of different kinds. They all operate with similar principles for the most part. They're all gaseous for the most part. So here's an example of a gaseous, a GEM, which a gaseous electron multiplier or gas electron multiplier. Basically, the operating principle for all of these is that any muon or charged particle will ionize the gas, and then these detectors are held at high voltages and will collect those ionized electrons, and we can report them as signal. So yeah, here's the GEMs, and then there's different types like the drift tubes. My favorite is the CSE. I work most closely with these ones. So this one's pretty large, but it's not the largest. It's Darin and I were talking about it earlier. It's probably an ME21 or 31. They can get larger than this, but these sit on the end caps, and they're also one of the large muon detectors. But yeah, so now that's kind of a close-up of each of the individual detector systems, and you can kind of see that even some of these chambers are large, and there's 540 of just this one alone. But now I'll walk you out to where they assembled the actual detector above ground, and you can see per scale a one-to-one image and see how large it is. So yeah, it was assembled above ground here before being lowered 100 meters underground in 15 different sections, each one weighing about 1,000 tons. The heaviest one was 2,000 tons, and it took over 12 hours to lower, or about 12 hours at least. But this is the hall that they constructed it in. So this was had to be very large to accommodate it. And then behind me, you can see an actual image of it. So this is a one-to-one scale. And it's sitting right above this concrete platform, which is actually mobile. And during technical stops, it'll be slid underneath the photo, and the large 100-foot hole or 100-meter hole is down here. Oh, can we? Okay. So we're actually walking out onto the platform right now. So we're standing above the large hole once we cross this threshold. And you can see the large equipment, the cherry pickers that are needed in order to go up and actually get access to the different detector systems. And then if we look over, just over here, I'll hit a button. I don't know if we actually explained where we are. So we're at interaction point 5 on the ring. So it's on pretty much the opposite side of the ring. It's very large. It's 27 kilometers in diameter. Yeah, so if this is a map, you can see here's the home base for CERN right here. This is the main site where our offices are and where the protons start. So actually, right here is LINAC 4. This is where the protons start. And then they go through a series of smaller rings before they get put into the large collider and accelerated for collisions. So here, let me show you a quick animation with this cool thing. So here, the protons are accelerated from a hydrogen gas. It's just heated up and into a plasma, actually, where they take off the electrons and we're left just behind with some protons. They go into a series of different accelerator rings. So this one's the SPS, which is the second largest. Once they get up to about 450 gigaelectron volts, they're injected going both directions into the Large Hadron Collider. And they put in about 3,000 bunches in either direction. Each bunch of protons has about 100 billion protons in them. Yep, so once they put them in, they accelerate them up to 6.8 TeV. And then when they're up to speed, they steer them into each other, and then we get collisions. And you can see at the very, very top, that's CMS. That's where we are. But we get collisions simultaneously in the 3 other main experiments. So Atlas is the other large general purpose detector. And then you have LHCb and ELISE, which are more focused on the large ion collisions or heavy ion runs. So when we get a collision of 2 bunches, there's 100 billion protons in each bunch. And so when they collide, there's 200 billion there. but we only get about 40 collisions. So the beam will last for a while. The fills can go up to like 12 hours, I guess. Yeah, so if only 40 are interacting, we can just catch them on the other side and then keep them going around. And that's how we're able to get collisions at all 4 different places. But that's currently. They're about to do an upgrade to the high Lumi LHC, where they're going to increase that to about 200 collisions every intersection. But they're going really, really fast. Of course, we need to get all that energy. So we go to almost the speed of light, 99 point many nines. I forget exactly the decimal point, but that means they're actually going around the ring, the full 27 kilometers, about 11,000 times a second. And then that means there are collisions at every 25 nanoseconds. So a lot of what I'll show you today is actually racks of computers meant to handle that and try and collect that data, keep up with the machine, basically.
Hey, Collin.
Yes.
So maybe as you're starting to head over there, because you probably should start heading to the underground.
Yes.
What country are you in? Where is CMS and then versus say Atlas?
Yes, good question. Okay, so right now in CMS, we're in France. We're in Cessy, France, at the top. But here at the main site where Atlas is actually Switzerland. So the border actually runs right through the middle of campus. So the vending machines over here are in francs, and over here they're in euros.
You said you gather data from all of the different points around the ring. So at each of those points is where you have the beams intersect?
Yes, yep. So for Atlas right here at point 1, and then over point 8 is LHCb here, over by the airport. And then there's Elise over in Saint-Genis, which is like the neighborhood I live in. And so each of these are full-fledged experiments that are very large, similar to us. And they have their own huge collaborations that have their own large control rooms and teams doing very similar things.
Okay.
I don't know. I hope I answered the question,
Yeah.
or if there are any more.
Yeah.
Okay.
You can head over. It's fine.
Okay. Yeah, we'll start making our way underground then.
There's another question here in the room. Go ahead.
What's on top of the ground inside the loop? Is that just regular cities and people live there and
Yes.
Yep,
Farms.
exactly. It's the ring sits about 100 meters underground, so you would never know that it's there. In fact, Elise is literally in a neighborhood. When you take the shift crew bus, you have to drive through a bunch of different houses until you get to the CMS, or I'm sorry, to the Elise experiment. And it's just a building. Aside from the big fence, you wouldn't know anything special.
wow, that's fascinating.
Actually, the apartment house where I live is right over the tunnel in Saint-Genis.
I had a question.
Other question, go ahead.
Yeah, so we're hearing stories sometimes about how different things can interfere with the data that you're given, like, you know, the pull of the moon on the lake and trains that go by. Is there anything that kind of has to stop when you guys are running the machine? Is there any sort of stoppage of life besides that, or
Generally, go ahead, Tom. I was going to say generally not, but what you're remembering is there was a predecessor to the LHC called the Large Electron Positron LEP accelerator to accelerate electrons and positrons, which are anti-electrons. There, they wanted to know the energies very, very accurately because we're trying to measure the mass of a particle called the Z boson. You guys have now probably been well familiar with that if you've gone through the QuarkNet. Okay. And they found that yes, tidal forces, where the moon was, and also when the train, the TPG to say going to Paris from Geneva goes by, they would adjust the currents would leave a little bit from the LH or the LEP magnets and accelerators and drop the energy or change the energy a little bit, and that mattered. And they had to compensate for that. So for LHC, we're not doing that kind of precision that matters as much, but I'm sure there's similar effects.
But maybe the tidal forces.
The tidal forces, maybe, yeah.
Yeah, I'd never heard that about the tidal forces from the moon, but I know at Fermilab in the US, they, in their little control room, they track the weather patterns, because if there's going to be a big thunderstorm running in or rolling in, thunderstorms charge the ground and your beam is underground, and so that will have effects. And so certainly weather is something that also needs to be tracked.
Especially if it has an impact on the power.
Sure.
If
That,
electricity goes down, then there's a bigger issue.
yeah.
But it's more of a, you guys take that into account in your data analysis as opposed to telling other things to stop. Like you wouldn't tell the train to stop going to Paris.
Oh,
No.
It's rather the operation.
It's more about the operations, yeah. So it's not something, I mean, as a physicist, I don't think about it affecting the data because I think, or I trust that the people operating the beam are doing their job and accounting for that. Yeah, we hope. It's more of a, yeah. The LHC is like a facility where their job is to create, deliver, focus the beam, all these things, maintain it. And then we, the experiments, receive that beam so we can do our experiment. But that's kind of like the difference in our jobs. We're doing the experiment, the science, so to speak, and LHC or CERN, they're creating and maintaining this beam for us to do that experiment.
And if I may add, we also have to make sure to protect society and people living above ground. So every, it's underground for many reasons, but one is also shielding from radiation.
Mhm.
Our magnet has a yoke around it and keep the magnet field contained, and it's also deep underground.
Mhm.
Doesn't matter for flat panel TVs anymore, but in the old days, those old teachers who may remember the CRT tubes, magnetic fields did a number on those, so to make sure not to have that. But I should hand it back to Colin. Looks like he's ready to go down.
Okay, yep. It's just I'm about to make our way to the elevators to go down. So just kind of show you some of the access security we have because CMS is actually lucky. We're the only experiment you can go underground during data taking, but that's because we can't go into the experimental cavern. We have a nice service cavern that runs parallel to it. So we're gonna make our way down there now. But first I have to go through these access points. So I have to have my personal dosimeter to make sure I'm not exposed to any bad radiation, and then also to identify who I am. So I'll scan this to let them know I'm going through, and then they also do a scan to check my irises to make sure it is me actually holding this ID. So, oh.
Did anyone ever watch the movie Angels and Demons?
Yeah.
I guess Colin made it through okay.
Yep, made it through.
I have just one comment on the Angels and Demons. You probably remember that this iris scanner was a nice, stylish device. We used that type. This one that you see actually on the screen is 2 generations older. Without spoiling the movie, this checks both irises and the blood circulation in them. That's what.
Okay.
So you have to be alive. This kind of
Or you have to have a complicated device.
Wait a minute. Hey.
All right, so we're starting at minus 97 meters underground. The elevator's coming up.
Yep. Yeah, so there are 3 floors in the service cavern down there. So starting at the very bottom, there's minus 97 meters, and then minus 88, and I'm not actually sure what the top one is. But yep, so this will lead the elevator down. This is, since it's about 100 meters, there are stairs, but the safety guidelines are actually to take the elevator in the event of an emergency, because you just get too tired and then the firefighters have to save you from the staircase. So they keep it over pressurized, so there's no smoke or any of the gases that might displace oxygen are kept out. So this is definitely the safest place to be in case of anything.
Yeah, it would be quite a hike because it's like 30 stories equivalent, 3 floors.
Yeah. But yep, so yeah, you can see we can go on to the 3 different floors. We'll go to the middle one where we'll see the counting room, and then we can also get close to the experiment and see where you would access it from. So
We
we'll
may
probably
lose
lose you
Colin.
here.
Might lose them, so we'll see.
At minus 3 meters.
Okay, we're going to just test your theory at minus 3 meters.
All right.
Okay, 2.2.
2.2 meters. All right, so at this point, while he's listening to the elevator music, did you guys have questions? More questions?
Any questions?
I mentioned the 30 floors because not that I would have done this in the old days, but yeah, it is quite the climb up those stairs to the top.
Darin, there's a question here in the room.
Yeah.
Go ahead.
How do you guys calibrate your detectors and how often do you do it?
Ah, that's a very good question. It has multiple answers because it depends which detectors and, so yeah, pretty much every detector system I think needs calibration. The ones that are probably the most critical are what are called decalimeters, the ones that measure energy. The electromagnetic calorimeter, the crystals that Collin showed you that are very heavy, those are very temperature sensitive. They're very radiation sensitive. We have lasers that pulse it and calibrate how much light goes through it so we can adjust that because we want to know when we measure energy, we really want to get it right. We don't want any systematic differences because we won't be able to find the particles we're looking for. So they're calibrated quite frequently. The hadronic calibrator also needs to be calibrated, but it's done a little less often. Along with calibration, there's also alignment. So those silicon strips and pixels have to be, aligned. We have to know where they are to like microns. So that's first done maybe with a laser system for the outer detectors, and then in situ by just using measurements of data from the collision. But pretty much all the instruments need calibration. See Collin there. He made it.
Okay. Yep.
You
We made it
survived.
to the bottom. Yes. So now we're at the -2 level in the service cavern. So here's one of the large, it's not the big hole that it was lowered down into, but this is one where large material is brought down. So you can see all the way up to the surface there. Here's a nice art installation showing representing data going up. That's what you see the little flashes are. But you can see this is one of the stairwells. Actually, so CMS is the main experiment here at the interaction point, but there are smaller experiments happening at CERN as well, away from the interaction points. One of them is Millikan, which is looking for milli-charged particles, which is based near the interaction point. It's actually up just a few flights of these stairs and then back into the woods, or not into the woods, into the rock. But then down below, too, we can see to the -3 floor, and there's a door there. I'm not sure how well if you can see it, but during technical stops or long shutdowns, they'll remove the door, and that's the experimental cavern. So that's they'll lower the material down this shaft and then through that door to get to the experimental hall. Yeah, so that's, I don't know if you saw that, we were walking around it at the top before we got to the elevator. But now we're going to go into along since the experiment's over there, we're walking along it, and now we're going to enter the counting room, which is one of at least two, I think maybe more racks of computers here. So
like two
in all
levels
of
of
these,
electronics.
yeah. So in these racks there are computers for all sorts of things. So as I was mentioning earlier with the muon system, a lot of the detectors are held at high voltage. So there's a lot of high voltage systems here that are controlling that and providing the voltage. As there's also other detector safety systems monitoring, and then also a lot of the trigger computers are here. So we collect, as I was saying earlier, a lot of data, too much. Every 25 nanoseconds, we're getting a ton of data, and we need to decide which one's relevant or not. So we have a 2-level trigger system. Level 1 is made of custom electronics that are situated on the actual experiment or in the racks closest to it.
Okay, look a little bit down right there. Yeah, go back. Go back.
Oh, if we can look over here actually. And
back where you were, the other side.
UF.
Yeah, well, yeah. So although it says Florida Gators, that's where I was before I went to Rice. That is the muon trigger for the end cap. That's our crate. You picked the right row to go down, Collin.
Perfect.
Because Rice is now taking care of that. That's where all the signals from the detectors, they go into this area, this underground service cavern. They go to other electronics and then they're sent to these set of boards. These actually find the muons very quickly and tell their momentum. I need to basically, Collin, if you can put like a Rice Owl sticker there right now, that'd be great.
Exactly. I should have brought one.
Go ahead.
Yeah,
Sorry to stop you, but I recognize it's great.
Well,
no, that's perfect. Thank you.
What are the blue cables there? They're
Good
particular-
question.
Yeah.
So, good question on both sides. The blue cables are actually optical fibers. That's how the data is coming in because we have a lot, as Colin said, a lot of data. In principle, the experiment could generate like terabytes of data per second. We're not getting terabytes into this system, but probably of the order of a few terabytes per second. And so there's each of those fibers is actually housing, if I remember now, 16 fibers each cable. So it's a lot of data going in each of those cards, and they basically represent geographically like 1/6 of a disk or 60 degrees slice. So there's like 12 sectors, we call them. And so this is the raw data from the muon detectors in the end caps go in there, the CSC that Colin just showed you. And then from there, we start to find trajectories, see if the muon went from one chamber to the next, and then because of that strong magnetic field, how it bent. And from that, we can use basically introductory physics 2 and calculate the momentum of a particle going through a magnetic field.
This entire room, as they walk around and show more and more of these electronics, the way you kind of think about it or remember it is all of these readout electronics from all the different subsystems. A lot of these are working together almost like a brain of sort that has to make a decision very, very quickly, like we said, on which collision events are good. And we, the physicists, decide what is a good collision or an interesting collision, and which ones are bad or not interesting. And so this whole room is working together very, very quickly to make those decisions and then store the data on disks that we will then later analyze as physicists do and write papers and make plots and whatnot.
That's a good analogy.
Yeah.
It's brains,
It's like a brain, yeah.
or at least the electrical signals, the sensors, and,
Yeah,
then there's
yeah.
some real computational brains up above.
Right. This is like the well, what this would be? Is it L1 trigger?
Yes, this is level
So
1 trigger.
so there's actually a couple triggers, and this is like the lowest level trigger. It works the quickest, but it doesn't do the most advanced thinking. But it's very, very quick, and that's the point.
Don't tell the level 1 trigger that.
Oh,
Say their feelings will get hurt. But they are running machine learning in it.
yeah.
All right,
I have
hand
a
it back to
question.
Colin. Oh, good question. Okay.
Oh, okay.
There's a question.
Is it easy to find if something goes wrong where that broken part may be with all those wires and diodes and I don't know. Is it easy to find where something is bad?
So when we were going
Needs to
through
be
the
replaced?
when Colin was going through the control, and that's part of the eyes. So we have displays we call data quality monitoring. There's I've called them zillions of plots, but basically if things go offline or somehow are not responsive or somehow just out of spec, a red box or light or error message will flash. And so that's the first way. And so we see, oh wait, one of those cards in that crate is not responding. And then it's up to the shift crew to kind of contact an expert if needed. They call them detector on call folks, and they'll see if they can diagnose it. Sometimes it just might be reboot a computer. It might need power cycle something, or in worst case, somebody's got to intervene and just do what the trip that Colin just did with a spare electronic card and carefully extract the non-functional one and insert the other one. But usually we can narrow it down. Now, if it's inside the detectors in the experimental hall, we're going to have to wait till whenever we're allowed to access it. We have to try to live and limp along.
Yeah, it's exactly like Darin explained. I pulled up this picture. I'll try to show it, but it's my phone. But basically, and I'll zoom in. Hopefully it makes it clearer. But these are some of the cards that are down there. We're probably not going to be able to see it too well.
But he'll have other ones to look at.
Sure, but one of those cards does not have the
Nope, sorry,
lights
that was me.
lit up.
Oh,
Yeah,
you're filming without the lights on. Okay.
Yeah. So
You can see it. Yeah, that's good.
yeah, but as Darin described, up here in the control room, you see, oh, there's an error with one of these modules in this approximate region. And then we tell the shift leader, we'd like to make an access, go down, at an appropriate time. You go down and then you look and it's like try to figure out, there they are exactly, the pixel feds. So you can see all the lights are lit up there.
Okay,
So they're
that
all
one's good.
working.
All right.
That one's good. But when we went down, yeah, there was one, just one in that whole rack there that the lights were not on. And we were like, okay, we'll double check with the documents to make sure it's this one precisely. But it's likely this one, and it was that one. So you pull it out and you put a new one in and get it working again, pretty much. Yeah.
Good question. Part of the work we have to do here.
Yeah.
Now it looks like they're looking at other cards. I guess those were the pixel feds, right?
Mhm.
How many pixel feds are there?
I don't know how many pixel feds there are. There's a lot, as we see here. But it's similar to the muon system we saw earlier. So I'm a pixel guy. I'm actually pixel doc often.
Okay.
So I'm one of the guys that gets called when there's problems here. But these pixel feds, oh man, fed, what does that stand for?
Front end driver.
Correct. Front end driver. That card is responsible for, it's the first, you could say, complex module that receives the information from the pixels and converts it to an optical signal where then it transmits it on. And so they also, somewhere in there, you'll see they have the same blue cables connected, or they should, if these are feds. They also have optical cables connected because they convert the electrical signal from pixels to optical signal that then gets sent further on.
But even from the pixel, you get optical.
That might be true. At some point, it goes from electrical to optical, and I can't remember if it's before or after the feds. So it's either coming into the feds as optical, coming out.
As far as I know, usually we gradually turn to optical in between the detector and the front end.
Yeah.
In order to not to have the ground loops.
So I was about to say, one of the reasons why we want it to be optical coming off of the detector is, again, that big magnet. And so as Zoltan, our director here, just mentioned that you can have ground loops if you have a loop of wire from your physics 2 class. You can induce an EMF and a voltage, and it can be very sizable. So we want everything optical so we don't have that potential to damage anything or have noise on our signal line.
Yeah, at this very point of the Earth, we are much more interested in physics than the BBC at top of the hour news.
Yeah.
All right, what do you got there, Collin?
Okay, since we're down by the experiment, one more complication for all the electronics is, I was talking about that strong magnetic field. We're still a distance away from it, but it's so strong actually that you can see the effect of it here with a chain of paper clip that I'm holding. You can see it's being pulled very far sideways. And this, even though we're quite a ways from it, I think there is it 3 meters of concrete between us and the experiment, or 7 meters of concrete. Sorry, so we're quite far from the experiment, but the magnetic field is so strong it can pull these paper clips. It even magnetizes the metal out here, so I can leave it just. Yep. It's not stiff. It's being pulled that way. And so you can kind of dangle this around and map the magnetic field as you walk around here. So sorry, that was kind of a shift in tone, but.
No, that's cool.
So no medical devices for anybody down there.
Yeah, absolutely not.
So again,
not with active implants.
Yeah, and again, when we first started installing here, we still had CRTs. And so I remember those displays because they were color, and the color was always going to just get screwed up because of the magnetic field just constantly distorting where the beam went. But,
well, actually, we often used in L3 the famous degauss button that the ordinary mortars usually don't push in their life.
I don't know if Collin told you when we were talking about the magnet, but that 4 Tesla magnet stores nearly 3 gigajoules of energy. And that's enough energy if you were to dispose of it too quickly to launch 3 of those 1,000-ton steel discs up to the surface from the bottom. So we have to carefully dispose of the energy when we ramp down the magnet.
I used to compare it with the terraforming
Another
capacity
question?
of the Boeing 747s.
Mhm.
Talking about disposal of energy, heat. I know y'all just make tons and tons of heat. Like, how does that affect what you do there? Like getting rid of that heat.
Definitely, I guess I'd start with that. So certainly starting from the electronics room in cavern where you're seeing here, all those electronics generate heat. So they need cooling. Often that can be air cooling, so there's strong fans blowing. In some cases, we might need water cooling. That might be actually most of the cases if I remember. So we do have to dispose of it because the electronics doesn't like to get too hot. In the experiment, it also generates heat, and we have even more challenges because some detectors want to be cold. They're generating heat, but they need to be, the tracker is at minus 30 C or something like that.
Something like that.
30 degrees Celsius below zero. And so we have to keep it cold, so that heat has to be taken out from that. So that's one of the limits on the electronics on the detector, because having the services to bring in the cooling, bring out the signals, interrupts with you trying to do your measurements. You want to have instruments there, but you have to have pipes. And actually, if anything, this high-tech LHC and CMS experiment, it's always limited by plumbing. It's just like your house.
We just had an issue with a leak in CMS that, I mean, I'm not on shift, so I don't know the exact details, but there was a intervention today, I believe, to go down and figure out how bad this leak was, or what exactly it was in the detector itself, but it was from the cooling system. Yeah.
So it's critical.
Yeah,
the
yeah.
cooling and the heat just removal, but it also is the bugaboo or whatever.
Yeah, and actually,
of our system.
we have a plan. Actually, we have a project to turn to liquid carbon dioxide cooling.
For the
much more effective for the next generation of detectors, the next tracker, the high granular calorimeter, the ETL, the BTL for the future. That's quite a big project now at CMS. Collin,
what have you got?
Oh, yeah. I'm just exploring more parts of the cavern. So we've exited the counting room, and now we've come to the end of this end of the service cavern. So through these doors are the actual this is the actual access to the experimental cavern. So because there is beam in the pipe right now, or at least they're injecting it, it's closed. You can't go in. So unfortunately, this is where we have to stop walking here. But this is how you normally go through. It's the same system. You have to scan your dosimeter again, and they scan your eyes. But then also, if it hasn't been cleared, you have to take an actual key that'll give you. And until that key is put back into the machine, they won't be able to turn it on again. So these are mainly just safety issues here because we can't be turning this on if anyone's in there. So this is one of the last safety measures for access, at least. But then this is now we're even farther closer. So again, you can just see the magnetic field. This is where we normally show everybody. Behind me also is, in this room is the gas mixing room. So I was talking about how the muon system is made of a lot of gaseous detectors. That gas is mixed in here, and then you can actually see the pipes that are here that are pumping it into the experiment, because it's not just left in there, it's actually flushed through the detector as it goes. So
That sign is not
okay.
a drunk person, that's a person who
What
passes.
gas?
Yeah. Question.
What gas?
Oh.
What gas?
There's a bunch of different types of gases. So for CSE, what we use is argon, CO2, and CF4. That's just the one detector. Generally, you want like a noble gas that's pretty inert, and you can easily take an electron off, because we're trying to ionize the gas and then take those loosened electrons and record them as signal. So most of the detectors will use stuff like argon or nitrogen. I don't know if there's any xenon used. And then there are other CO2 or some other organic molecules for things like quenching, so to reduce dead time or prevent extraneous like sparking because of the high voltage system. And then also there are gases to help prevent the aging of the detector. So the one I study, CF4, helps etch away any organic compounds that might follow. Oh, we can go in? Ah, okay. We can actually enter the gas room. Sorry. I'm learning.
Gas
I can
just
go in.
lose one electron per collision? What if you lose multiple?
You do lose.
For the electrons,
Yeah.
ionizing? Yes, depending on how energetic the particle is, it'll release multiple electrons, and then those electrons are pulled towards the high voltage wires. And then the idea is actually we hold it at such a high voltage that when they get close to the wires, they cause an avalanche. So as they move, they start knocking out a ton more electrons. So if you release like 5 electrons, hopefully they turn into 500,000 electrons, so you can register a good signal. Understanding your detector geometry, and then studying the response to different energies for particles, you can get a gauge of what your signal is going to look like. We don't expect like 1 particle, 1 electron. We need more than 1 electron to sense it.
Collin, the
Yes.
name GEM stands for what again?
Gaseous electron multiplier.
So multiplier is the key word there.
Well,
Yeah.
we have to multiply. One single electron's charge is extremely small. None of the electronics would be able to detect it. You have to multiply it, usually 10 to the 6, something like minimum, in order to get that charge is still very tiny. We still need very, very, very sensitive electronics, but that's already something that technologically possible.
Right.
I mean, one of those CFC chambers, for example, you could think of it as a Geiger tube, so a wire with a voltage, and that's the amplification, so you can have a measurable signal. But those CFC chambers have like 6,000 wires, and there's 500 of those chambers. So there's a lot of wires just for one system, and there are other muon systems too.
CO2 is to make sure that.
Yeah, so right now we're looking at the CSC ones. So this is where our gases mix. So I know for sure it's those 3 gases.
And actually, we have a large project to phase out the greenhouse gases.
Yeah, because he mentioned CF4, and that's actually something we're trying to get away
that's
from.
one of the most cruel one.
Yeah.
So actually, that is a huge project to get rid of these gases. The problem that these gases probably the best for the detection. So we have to find a good compromise.
Aren't you doing tests of CSCs with the different gases?
Exactly. Yeah. So we're currently using 10%, but we're trying to reduce it to maybe down to 5% is what I'm looking at. And then also the gas group here at CERN have implemented a recuperation system. So the gas we put through the chamber, instead of just letting it go, we actually try and filter back out that CF4 and use it again. And so I'm studying to make sure that remains well behaved when we do that. So we're trying to cut down significantly our use of CF4.
And the RPCs as well, I think, have a recirculation system because they have to recycle their gases as well.
Yes, they're not quite using CF4, but I know that it's another fluorinated molecule that's not good for the environment. So yeah, we don't want
leaks into plumbing either. The gas.
Well, I'm not a gas or a muon guy, but the story I was told is that we had to use those gases because the technology for a different gas, say CO2 or something, just wasn't available at the time of the construction of this. But now, hopefully, with the upgrade,
we're trying. I mean, you have multiple challenges. One is to get that amplification, so that might be one set of gases. But the LHC, as Collin said, collides beams every 25 nanoseconds, 40 million times a second. The beams are crossed. So detectors have to be fast. So then you want something in the gas that makes it a fast signal as well. And then on the other hand, we're going to run this for CSCs, it's already been like 2 decades, and we're going to run another 2 decades. You know, they can get coated if you have too much carbon or other things in the gas. It can coat the wires, and then it'll be less responsive. So you need to, again, optimize the gas mixture so it doesn't age on the gas. It doesn't have too much deposits. In fact, we've taken out chambers and cut the wires off to put it under a microscope to examine just how they are aging.
Wow.
Oh, good. Found the toilets. It's important underground. By the way, guys, where he is underground.
These toilets go.
So we're in the control room now. I am anyway, not Collin. But where he is where the first control room was, is downstairs underground. So when we first started commissioning this experiment, we didn't have an above ground control room, and we weren't commissioning, say, all of the detectors, but some fraction of them. We were living, 8-hour shifts, but usually longer, down, the 30 floors down, an elevator trip. So you definitely needed the toilet because you didn't have to keep going up and down. You had sometimes took your lunch down there. But yeah, the beginning days, just trying to get CMS operating, getting commissioned. We were actually had the control room down there with not quite where the electronics are, but there was a little side.
But obviously, you had to be very close to the electronics, very close
So
to
you
the
can
hardware.
intervene and reboot
Exactly.
things and pull cards out because you're trying to, along with the detector, you're trying to make sure the electronics are starting to work right.
But once we started the first run, this room became very, very silent, very quiet. We often went down to work.
Good place to
hide
escape
away.
and have a nice
Exactly.
quiet,
That I
thinking
love
place.
that place.
Yeah.
The old control room.
The old
Yeah,
control,
after the
well,
people had moved
the
out
underground
to-
control room.
yeah.
Today, it became probably the noisiest place. Exactly the opposite. The new CO2 pumps will be installed there and people hide away.
Where are you now, Collin?
Muted.
Collin, are you still with us?
You're muted, it looks like.
Yeah.
Hi, sorry, yes, I'm here. So we just went up a floor in the service cavern, and so here's where we're looking at, it cools the helium to keep the magnet cold. So that's what this large apparatus is. It cools it and then pumps it through and the pipe up there through the cement wall here and towards the actual experiment. So I just wanted to catch this real quick before we ended there. So
this is a giant refrigerator.
yeah, so there's. Oh, and this is the power line. Okay, so this is where all the remember we had 18,000 amps going through it. So these are the power lines that are supplying that power to the magnet as well.
So I thought I might show this.
Yeah.
We didn't really talk about it.
Just a little moment. Let me put you on
Share
the
screen.
screen. Yeah,
There we go.
go on, sir.
So this, I'll show a picture, and then maybe, does anybody want to guess what this device is? It's a safety device for when you're working underground.
Gas mask.
Oxygen source?
It's an oxygen source, correct. We call it a self-rescue mask, and when you're in certain areas of the underground, it's a necessity to carry this on you. You just kind of wear it around your hip. It's like this big belt, and it kind of clunks as you walk around, but you have to be trained how to use it. There's a tab at the top, and in the event of...
Don't open now.
Never open. It's a one-time use. But in the event of a gas leak, and the oxygen is pushed out of the atmosphere around you, alarms will go off, and you flip the tab, and that mask pops out, and there's a way you put it on, and it's kind of like a snorkel, actually, because you have to put it in your mouth and put a nose plug on, and then you breathe through that device, and it delivers oxygen through a chemical
regenerates
process.
Oxygen from the exhaled
from your exhaled air. Yeah, it doesn't. It's like a, I don't know the term, but it's its own environment. So no outside smoke or helium or whatever those gases are. None of that's going to get in there and get in the mix. It's just you exhaling, and there's a chemical process in there that delivers the right amount of oxygen. So you have about 30 minutes of breathing time.
That's a quite important 30 minutes.
Yeah.
Probably you have already realized especially when Collin talked about the key access, that we have several levels of safety. We do not rely on only one process when we want to save the life of our colleagues. For the evacuation, we also have several possibilities. The easiest is to go back to the elevator that you have just seen, but we have another backup elevator. But if both would fail, and you wouldn't have any other choice, you could walk down in the accelerator tunnel towards the next access points that are somewhere around 3 kilometers away, and that's something like 30 minutes. So all these self-rescue masks are specified such that they should provide oxygen enough for walking away up to the next access point. But this is the last resort.
Yeah, we don't want to have to use that.
We never had to use them at CERN. Once I used them, I was a trainer of these masks, and I had the possibility to open a real one and use a real one. But I was in that very special situation for the training. But I never heard about any real.
And the reason you need the oxygen, by the way, because the LHC, as was explained, I think Colin probably, it's really cold, those magnets that bend the protons around. It's below the liquefaction point of helium, so 2-point-something degrees above absolute zero. That's all with liquid helium. If it warms up, what does helium become? A gas. It's going to displace all the oxygen. You can't breathe. So that's why we have these masks, because it's a hazard. It's an oxygen deficiency hazard. And yeah, that's a pretty realistic training that we have to go. We just don't have to run it, but you have to put it on in the right amount of time so you don't pass out. And
Well, according to the safety rules, if you want to access these zones in the tunnel, for example, you have to take them with you.
Yeah.
You don't need to wait until you have to search for.
But you've made it back, Collin. We're just in time.
Welcome back.
Yes.
All right. Well, we're probably rubbing it up at the top of the hour. You've got a. Oh, by the way, so you probably have your seminar coming, but it's just in time. Were there any last questions?
What are you afraid of falling on your head? That's why you got to wear a helmet.
Well, especially during the shutdowns, people are using, if you're going to the experimental cavern, they're using cherry pickers, so they're way up high, and if you're walking beneath them and they drop any equipment, you need to have this. All of those different floors we were walking around on the surface cavern are false floors too, so somebody could be, there's not like a hard ceiling above you, so maybe something falls through there. Yeah, so it's important, don't want to take any risks. And then you also have to wear safety shoes because people are moving around heavy equipment. If that falls, you don't want that to crush your feet. Yeah, it's just best to play it safe and sorry.
Usually I have a very profound answer on this question.
Yeah.
Even I use the helmet and the safety shoes, but even though I'm a very small person, the answer is that this is not a very, very dangerous situation, very, very dangerous place. It's just like any other industrial installations, but we are very popular. Even the smallest accidents would make us to land up on the front pages of the leading newspapers, and we want to avoid it. Yes. That's the reason. We are very strict on the safety rules.
We're publicly funded from many different
that's the other thing.
I mean, yes, we want to be safe, of course. We take it very seriously, as CERN does. We want to make sure that we can focus only on the science and not
have a lab closure.
Yeah, not have a lab closure or excessive safety courses to remind people to wear a helmet or something like that.
And just to explain why we didn't keep anything. So obviously we are very strict on this. Our safety rules are extremely strict, and we enforce these rules to be kept by all our colleagues. And the reason is this, that we just want to concentrate on physics instead of explaining why we had in trouble.
So by the way, a different topic, because I know we've got to wrap it up probably, because I probably think your seminar speaker's there. You're going to go from quarks all the way up to and Higgs bosons to astronomy and the universe. But there's actually a connection, because the universe had to start. Universe had to start somewhere, right? A big bang, and so it's essentially infinitely dense, and that was when all the laws of particle physics and everything and stuff we're still trying to figure out how it works. It's kind of our aim, is understanding these fundamental forces, how they're connected. How did the universe inflate quickly at first? What field was responsible for that? So even though you might be next hearing about the biggest structures in the universe, it has a connection to these particle collisions, which is really either deep inside a star or a neutron star, but also from the beginning of the universe itself. And I guess I'll see if there are any more questions, or you can cut us off if you need to run.
I think we want to thank you all for allowing us to have a bit of an insight in the CMS experiment. For me, it's certainly fun to see the new control room. I have not seen that one, so so I think a round of applause for. think indeed one central theme that whether it's CMS or the James Webb Telescope or other experiments is that these are big collaborative efforts, and it's really always extremely exciting to see many people try to work towards a common goal of exciting science. And you know, it's good to see folks from Rice on the other side of the line here. And safe travels back to you guys. And thanks again for allowing us to visit the experiment. All right. Houston is signing off.
Thank you.
Thanks everybody.
You're welcome. Bye.
Bye.